Good day, everyone. My name is Lawrence A. Cornello, a BSc CE3 student from Bicol University, Pulangi, and today I will be discussing about multimedia processing. Let's proceed the code. So first, we import all the libraries we need. So NumPy for numerical operation, Librosa for audio processing. This is a specialized library for music and audio analysis. Matplotlib for plotting, CP, CP for the Butterworth filter, OpenCV or CV2 for image processing, and IPython.display for playing audio in Jupyter notebooks. First is below the sample audio using Librosa, that trumpet y sr is equal to librosa.load file path sr. So this load a built-in trumpet sound. The function return two things: y, which is the audio signal as an array of amplitude shift values, and sr, which is the sampling rate in hertz. We then plot the waveform using Librosa.display wave show. So this show how the audio amplitude changes over time. So the x-axis is time in seconds and y-axis is amplitude. Okay, so that's our code. Okay, so here, so you can see the attack, sustain, and decay of the trumpet sound. Okay, now, so we compute the short time Fourier transform or STFT. So using Librosa.shift, this breaks the audio into small time windows and computes frequency content of each window. We convert the result to decibel using amplitude to dB. Then the spectrum is a 2D plot where the x-axis is time, the y-axis is frequency on a log scale, and the color represents how much energy is at each frequency. So brighter color means louder frequency. This gives us a complete picture of how frequency change over time in trumpet sound. So this one is the spectrogram. Uh, so now we create the Butterworth filter. We define a function called butter low pass filter. So this function takes the audio data, cutoff frequency, sampling rate, and filter order. So it calculates the Nyquist frequency, which is half the sampling rate. Then it normalizes the cutoff frequency and designs a Butterworth filter using butter. Finally, it applies the filter using I filter, L filter, and returns the filtered audio. So we set the cutoff frequency to 1000 hertz, then apply to the filter, then we plot the first 2000 samples of both the original and filter signal. So the original has more high frequency content while the filtered version is smooth because frequency above 1000 have been removed. So this makes the trumpet sound more muffled or darker. Uh, and the so here is the original versus the low pass filtered audio signal. Now, so loading in this. Now we switch from audio to image processing. We load the grayscale image code. So I upload CompuStrek using cv.imread with the grayscale flag. We check if image loaded successfully. So here. So yeah. So the image got load. So we compute the 2D fast Fourier transform of the image using np.ffp .ffp2 image. Then we use ffp shift to move the zero frequency to the center. So the magnitude spectrum shows how much energy exists at each frequency in the image. Low frequency are in the center and high frequency are toward the edges. So here is the magnitude spectrum. So we convert the log scale using 20 times np.log because the range of values very large. The resulting magnitude spectrum looks like a cross or star pattern where bright spots represent strong frequency components. So here's like a star pattern. Now, so we apply a Gaussian blur using CV2 dot Gaussian blur with a 9 by 9 kernel size. This is a low pass filter for images. It removes high frequency details like sharp edges and fine texture, leaving only the low frequency smooth parts. Then we display the original and blurred image side by side. Note how the blurred image looks softer and less detailed. So here, so this is the blurred image, and last is we the noising with median filter. So we add random Gaussian noise to the image, sim simulate a noisy photograph. Then we add a filter median blur with a filter by 5 by 5 kernel. The median filter is excellent for removing salt and pepper noise while preserving edges. We display three images side by side: the original, the noisy version with graininess, and the denoised version. So the denoised image looks much cleaner while keeping the important details like edges and contours. So, so this is the original image, the noisy image, and the denoised image with median filter. So that's all. Thank you.